For a long time, chip design in the US followed a fairly straightforward rule. Build the most powerful, efficient, and scalable processor possible, then figure out where and how to sell it. Regulation existed, but it sat on the edges of engineering decisions. In 2026, that separation is gone. Export controls are no longer a policy issue handled after a chip is designed. They are now one of the most influential forces shaping chip architecture itself inside the United States. Export controls place limits on which chips can be sold to certain countries, what performance levels are allowed, and which manufacturing techniques can be used. While these rules are often discussed in terms of geopolitics, their real impact is happening deep inside engineering teams. Designers now treat regulatory limits as fixed design constraints, similar to power budgets or thermal limits. This has fundamentally changed how chips are planned from day one. One of the biggest changes is how performance targets are set. In the past, teams aimed for maximum possible compute, memory bandwidth, and interconnect speed. Today, those goals are often capped intentionally. Engineers design chips to operate within specific thresholds that remain compliant across multiple markets. Instead of pushing absolute limits, they focus on delivering strong real-world performance without crossing regulatory lines. This has shifted optimization away from raw peak numbers and toward efficiency, workload tuning, and architectural balance. Modularity has become a central design strategy. US chipmakers increasingly build processors using modular blocks that can be enabled, disabled, or scaled differently depending on the market. AI acceleration units, memory interfaces, networking fabrics, and even clock domains are designed to be adjustable. This allows companies to create compliant variants without redesigning entire chips. What looks like a single product family on the outside often contains multiple regulatory configurations under the hood. Memory design is especially affected by export controls. Many regulations focus not just on compute power, but on how quickly data can move. High bandwidth memory, interconnect speeds, and parallel data transfer have become sensitive areas. As a result, designers are rethinking how memory is structured, accessed, and shared across processing units. Clever architectural choices can reduce measured throughput while preserving practical performance, allowing chips to stay within limits without becoming uncompetitive. Interconnect architecture has also changed. Chips increasingly rely on internal and external communication fabrics to scale performance. Export rules that target interconnect speeds force designers to rethink how components talk to each other. This has led to more localized processing, smarter task scheduling, and reduced reliance on wide, high-speed links. The result is a shift toward efficiency-driven scaling rather than brute force connectivity. Manufacturing considerations are now tightly coupled to design as well. Certain fabrication nodes, packaging methods, and advanced techniques are restricted for specific markets. US designers are building chips that can be manufactured across a wider range of domestic and allied foundries. This means tolerating variation in process technology and avoiding designs that depend too heavily on a single cutting-edge node. Portability and resilience are now design goals alongside performance. Export controls have also lengthened planning horizons. Chip development already takes years, but regulatory uncertainty adds another layer of risk. Teams now design with multiple future scenarios in mind, anticipating possible rule changes. This often means delaying or softening features that could become problematic later. While this slows down visible innovation, it reduces the chance of producing chips that cannot be sold widely. AI chips show this transformation most clearly. AI accelerators are among the most tightly regulated components due to their strategic importance. Instead of building ever larger, more powerful AI processors, US firms are focusing on specialization. Chips are optimized for specific workloads, using techniques like sparsity, quantization, and model-specific acceleration. This allows meaningful AI performance without crossing regulatory thresholds tied to generalized compute power. Software has become a critical partner in this process. When hardware performance is capped, software optimization becomes more valuable. Compiler design, model optimization, and workload scheduling now play a larger role in delivering performance gains. Export controls have indirectly increased the importance of software-hardware co-design as companies look for gains that do not trigger regulatory limits. Internal collaboration has also changed. Legal, policy, and compliance teams are now involved much earlier in chip development. Engineers are expected to understand regulatory definitions and thresholds. This cross-functional approach slows decision-making but reduces costly redesigns later. Policy awareness has become part of engineering literacy inside US chip firms. Another major impact is market strategy. A chip that is slightly less powerful but broadly sellable is often more valuable than a high-performance chip restricted to a narrow set of customers. Export controls have shifted success metrics away from technical supremacy and toward market accessibility. Design choices increasingly reflect where chips can be sold, not just how they perform in benchmarks. There is also a long-term strategic effect. Export controls have highlighted the risks of global dependency. US chip designers are prioritizing architectures that can be supported by domestic supply chains and local manufacturing initiatives. This may increase costs in the short term, but it reduces exposure to geopolitical shocks. Design resilience has become part of national and corporate strategy. Importantly, this environment has not stopped innovation. It has redirected it. Constraints force creativity. Engineers are finding new ways to extract efficiency, reliability, and scalability within tighter boundaries. Some of the most sophisticated chip designs today are not the ones with the highest raw specs, but the ones that deliver consistent performance under complex regulatory and supply conditions. In 2026, export controls are no longer an external hurdle for US chip makers. They are embedded into the DNA of chip design. Architecture, performance targets, memory systems, manufacturing choices, and software integration are all shaped by regulatory reality. The result is a quieter but more deliberate era of innovation, where success depends not just on technical excellence, but on designing chips that can exist, scale, and compete in a world where policy and silicon are inseparable.